We know about dot product. If I take the dot product of two vectors, I get a number, I get a scalar, and I know that that number represents how much the two vectors point in the same direction. So two vectors that kind of point in the same direction, the dot product is positive. If they're perpendicular, the dot product is negative. If they're pulling away from each other, then the positive dot product, zero dot product, negative dot product. If they're kind of pulling away from each other. Perpendicular, I get a zero dot product. All right, if I take the dot product, which is kind of like multiplying two vectors, if I take the dot product of two vectors, I get a scalar. Another way of multiplying two vectors is to take the cross product. The cross product of two vectors gives you a vector, as opposed to the dot product, which gives you a number. So let's learn about cross products now. Cross product of two vectors gives you a vector, and I need another pen. The vector that it gives you is perpendicular to the two vectors you cross product. So if I cross product pencil on Sharpie, I get perpendicular to the pencil and to the Sharpie. That's the direction of the cross product vector. The magnitude of this cross product vector is dependent on the angle between these two and how long these vectors are that you cross product. But let's take a look at the formula. And the formula that we're going to look at, which you can just see there, well, I haven't finished it yet, but the formula that you look at is given in 3-dimension. When we're cross producting in this course, when we take the cross product of two vectors, we mean two 3-dimensional vectors. The result is a 3-dimensional vector that's perpendicular to the ones that we cross product. So our formula is defined by that in 3D. It makes sense that we can't cross product stuff in 2 dimensions, because if I had two vectors in 2 dimensions and I cross product them, I'm supposed to get a vector that's perpendicular to both of these. It would have to point straight out of the page. Doesn't make any sense to cross product two things in 2 dimensions. Anyway, taking the cross product, here's our formula. It's like multiplying. When I take vector A cross product vector B, here it is, our formula component-wise. Now, I had to finish it off here. They're all AB minus AB, AB minus AB, AB minus AB. That's if I'm thinking of vector A as components A1. Let's put that in there. That's if I'm thinking of vector A as the vector A sub 1, A sub 2, A sub 3. And likewise vector B as B sub 1, B sub 2, B sub 3. Let's just put it in there for completeness. So that's the component formula, which we're going to go over, has to do with all the components, the A1, A2, A3, and the B1, B2, B3. And they're all AB minus AB. Now the first component, this is the way that I'm going to, rather than just throw down the formula and say, here it is, what I want to do is kind of get a pattern to it, because it's kind of a complicated formula to remember if I don't think about it in terms of a pattern. But the first component here, before the comma, doesn't have any ones in it. It only has 2s and 3s. So it only has to do with A2s, B2s, A3s, and B3s. And it goes 2, 3. It goes to 2, 3, and then 3, 2. So first component, no ones, so only 2s and 3s, and it goes 2, 3, 3, 2, so higher and then lower. Likewise here, this middle one doesn't have any 2s in it. It's going to go 1, 3, did the same thing before, 1, 3, 3, 1, AB minus AB. I'm going to fix this, I'm going to change this, this isn't right yet. Let me put that at the end. But let's get this last component. It's the third, doesn't have any 3s in it. So it's going to go 1, 2, 2, 1. 1, 2, 2, 1. So up and then down. Okay, I said that I still have to fix this one. The middle component has a negative in front of the whole thing. That negative is the thing that if people misremember or screw up the formula, it's that negative that usually is the problem. But we'll have ways of checking to make sure that you did the thing correctly. Now, instead of throwing a negative with the whole bracket against the middle component, I guess I could have written it as A3B1 minus A1B3, just like multiply the minus sign through in my formula. And maybe you might want to do that if you think that that makes it easier to remember the formula. I like the pattern of 2, 3, 3, 2, like high, low to high, high to low, low to high, high to low, that kind of thing. And then just remembering the middle term has a minus in it. Anyway, there's our formula. That's as it is defined component-wise. Another way to think about it then is those people that know how to take the determinant of a 3 by 3 matrix can think of the cross product of two vectors as the determinant of this matrix. So A cross B, those are vector I, vector J, vector K. So vector I is the vector 1, 0, 0, vector J is the vector 0, 1, 0, vector K is the vector 0, 0, 1. And you'll note, so when I take the determinant, you'll notice that if I take the determinant across the top row, which is how you're really supposed to do it in this case, that it would be plus the I times this little determinant, which would be A2 B3 minus B2 A3. That's this first piece. The second one would be minus, because it's the second piece in, right? The pattern, the checkerboard pattern for taking determinants, plus, minus, plus, would be J times minus J times A1 B3 B1 A3. So I get this same pattern. If you already know how to take the determinant of a 3 by 3 matrix, sometimes this is an easier way to remember the formula. If you're not so familiar with linear algebra and determinants are not so comfortable, then maybe this sort of algebraic way is the way to remember the formula. Either way, we've got our component-wise way of expressing the cross product of two vectors. And you get a vector, you get a 3D vector. Okay. What I've said so far is you get a 3D vector, and I promised that 3D vector is perpendicular to A and perpendicular to B. I haven't proven anything yet other than just sped out, here's the formula. Let's look at an example first before we investigate some stuff. So I want to calculate the cross product of these two vectors. So 1, 2, 1 cross product 2, 0, 1. So to be honest, if you weren't looking at me, I'd use the determinant way. I think it's easier. But let's use our formula way here. So the first component, and show it's perpendicular. The first component is going to be 2, 3. So 2 times the 1, that's 2, minus 1 times the 0. The second component I know has a minus, so I'm going to put that in right away. And now it doesn't have anything to, it's only the first and last. So first times the last, that's 1, minus last times the first, that's 2. Now the last component only has 1s and 2s in it. The third only has 1s and 2s in it, no 3s. So that's going to be 1 times 0 minus 2 times 2. All right, there's a ton of ways that I could have screwed this formula out. Multiplying things wrong, putting in the wrong formulas. Let's simplify this and see if I'm correct. When I simplify this vector, I'm getting the vector 2. This is going to be minus 1 with a minus minus. So 2, 1, minus 4. Now, this, if I did the formula correctly, is supposed to be perpendicular to both vectors. How can I tell if it's perpendicular to this 1, 2, 1? Well, in other words, show that my result, it's really here, show my result is perpendicular, is orthogonal to each of these vectors, to both of those vectors. But I can also think of it as me checking to see if I did all my math right in the formula. That's probably a more useful way to think about it. Well, what I'm going to do is I'm going to take the first vector and dot product it against the second vector. Now, dot product is a lot of an easier formula. And if I get 0, it's perpendicular to that vector. First times first, that's 2. Second times second, that's 2. 2 plus 2, third times third minus 4. 2 plus 2 minus 4 equals 0. Yes, it's perpendicular to the first vector. All I got to do now is, well, dot product my 2, 1, minus 4 with the second vector. That one's going to be even easier. Let's finish it. And probably by the time I type this in, you've already checked and you'll see that it is perpendicular. Because I get 2 times 2, 4, plus 0, minus 4, 0. So my answer is perpendicular to each one of those vectors. So that, well, that shows that my result is orthogonal. And it checks all my algebra and it checks all my plugging into the formula correctly. Okay, that's an example that my answer is perpendicular to both vectors, but I want to show that that's true for any vector. So I'm going to use the same idea here. I'm going to take vector A. So let's take vector A, no. And I'm going to cross product it I'm going to take vector A and cross product it with the A cross B vector. And I guess so this is what I want to do. I want to take vector A and cross product it with my resultant A cross B vector and show that it's equal to 0. No, I want to dot product it because I want to show that it's perpendicular. So that's going to be first times first plus second times second plus third times third. Okay, first times first is going to be equal to, so it's going to be this piece times A1. I'll just distribute it across. Plus this piece times A2. I'll distribute it across. I'll keep them in order. And plus minus that bracket, I can just clean that up like that. Now plus this piece times A3. And now, if this all cancels out and equals 0, which it does, then it's perpendicular. Then A cross B is perpendicular to vector A. And I mean, I'll let you, if you want, pause the video, but you can see that some things, so here's the A1, A2, B3. That's minus this, cancels out this piece. So this plus and this minus cancel out. Here's minus 1, 3, 2. Here's a plus 1, 3, 2. Those pieces cancel out. So if you do the canceling, everything else cancels out to be 0. So that we have it in our notes here, let's put this first piece back here, which is the A1. Okay, so do I have to go through and also check for the vector B? So this would be a B1, B2, B3. Yeah, you could, to show it's true for any of the vectors. But let's, instead of like going through the math and like brute forcing that out, let's take a look at the actual formula, the cross product formula, and see what happens if so I'm going back up here. What happens if I take vector A and vector B and switch positions? So instead of going A cross B, I'm doing B cross A. Well, that would mean that whatever number was in this first spot would switch with whatever number was in this first spot. All the A's would become B's and all the B's would become A's, in other words. So if the A's become B's and the B's become A's, then that term would just be the negative of what it is now. Likewise for all these other pieces. So if I take A cross B and A cross B and B cross A are just the negative of each other. So again, if I do A cross B, I'll get a vector that points perpendicular out this way, and if I do B cross A, I'll get a vector that points perpendicular the other way. It'll have the same magnitude, it'll just have the exact opposite direction. They'll be parallel, but one will be plus and one will be minus. So if it's perpendicular this way, it's perpendicular that way. So true for any vectors, yes, I always get a vector that's perpendicular to both vector A and vector B. Now, what about here if I take A cross A? Well, if I take A cross A, let's go back up to the formula again, then all the B's are A's. So this would be A2, it'll be A1, A2, A3, A1, A2, A3. So this will be A2B, no, it'll be A2, A3 minus A3, A2. All of the components ends up being 0. So if I cross product a vector with itself, I get the 0 vector, which kind of makes sense, right? If I'm taking a vector that's the same and I'm cross producting it with itself, and I'm asking the math, give me a vector that's perpendicular to those two vectors. Well, it's the same vector. So the math, there's a whole circle, there's a whole infinite number of vectors that are perpendicular to both those vectors because they're the same vector. So the math, how does the math express that as an answer? It gives me this 0 vector. Because it can't give me one vector, it can't give me all the vectors, so it just gives me the 0 vector. And the formula bears it out that it is the 0 vector. But let's be careful here, it's the 0 vector. So I made sure I put a 0 hat on it. Now, what if the vectors are not the same vector, but they're parallel vectors? So one's a little bit smaller than the other. If I cross product two parallel vectors, you can check this with the formula. You will also get the 0 vector. So the cross product of two parallel vectors is the 0 vector. We'll see that in some properties further on as we go. Now, we have two, I'm going back to the other way of kind of multiplying vectors, the dot product. The dot product gave us a number, the cross product gives us a vector. We had our component dot product formula, first times first plus second times second plus third times third, or fourth times fourth, right? Dot product, I can take the dot product of vectors in any dimension. Cross product, our formula is restricted to 3 dimensions. But we also have, so we have a component formula for dot product, first times first plus second times second plus third times third, and we have a component formula for dot product, and we have a component formula for cross product. That's the one we made up there. So We also have a dot product formula, magnitude of A, magnitude of B, cos of the angle between them. There's a similar trig involved formula for the cross product. So, and here it is as given, that A cross B is given as the magnitude of A, magnitude of B, sine of the angle between them. So it has to do with the angle between them. Times U, and U is a unit vector perpendicular to A and B. So that gives us its direction. So the magnitude of A cross B is magnitude of A, magnitude of B, sine of the angle between them. Oh, so that also, okay, we're going to prove this is true, but like assuming it is true, that makes sense why if I take two parallel vectors, the angle between them is 0, magnitude of A, magnitude of B, sine of 0 is 0. So I get 0 times the unit vector perpendicular to both of them. Even that formula is telling me I get the 0 vector. We have to prove this formula. Let's prove this formula. So I know that the vector I get is perpendicular to A and perpendicular to B. When I take A cross B, it's a vector perpendicular to A and perpendicular to B. We proved that up here. So really I just need to talk about its magnitude. So if I can prove that the magnitude of A cross B is equal to magnitude of A, magnitude of B, sine of the angle between them, I would have proved that formula. So let's take about the magnitude. And to make the math easier, instead of proving the magnitude of A cross B is equal to, I'm going to square both sides. So if I can prove the magnitude of A cross B squared is equal to magnitude of A squared, magnitude of B squared, sine squared, then I've proven what I want to prove. So this is my sort of goal. Once we've proven that, we've proven our assertions, our other definition, our trig involved definition of the cross product. So I want to prove this. Now, this is going to get algebraically ugly. It's going to require a lot of brute force. Let's go up here and grab this is our definition of what, that's A cross B, component-wise. So if I want to prove this, if I want the magnitude of this, so this is going to be the, let's call this the left side. The left side is equal to the magnitude of this piece, but that's just equal to, the magnitude squared is just equal to the dot product of it against itself. There's the left side. Here's where I said brute force is going to be pretty tedious. I'm going to have to go first times first plus second times second plus third times third and brute force that all out. We can do it, it's just a lot of algebra. Let's take a look at the right side. In the end, I want to make right side equal to left side, but the left side here looks like it's like a lot of algebra, which we could do, but I don't want to do it right now. Let's take a look at the right side. So the right side is going to be magnitude of A squared. So that's going to be A dot A. So that's, magnitude of A squared is going to be A1 squared plus A2 squared plus A3 squared. Likewise, magnitude of B squared, it's going to be B dot B, or B1 squared plus B2 squared plus B3 squared, giving me an undo. Now I just need this sine squared theta. Well, I'm going to replace sine squared theta as 1 minus cos squared theta. Why am I doing that? Because I already know what cos squared is, or cos squared is connected to A dot B. So note that if I do A dot B, I should put vector hats on them. A dot B, which I know is equal to A1, B1 plus A2. So let's A1, B1 plus A2, B2 plus A3, B3. And that's equal to magnitude of A which is just the square root of this piece here, magnitude of B, which is just the square root of this piece here, cos of the angle between them. So this is me just like rewriting the dot product formula with cosine. That means, since I know this is true, that means that the cosine, I'm just solving this for cosine, that means cosine of the angle between them is equal to the dot product, and I'm writing these all out component-wise, divided by those two magnitudes. Okay, but I want cos squared. So cos squared is going to be, I'm just squaring both sides of this expression. Oh, nice. Squaring both sides of this expression gets rid of those square root signs. So if I square both sides, I get rid of those square root signs. That's what I get. Okay, that means I can write this right side. Instead of writing cos squared, I'm putting in this piece here. Alright, now I'm trying to prove this. I've got left side written with all A's and B's, 1, 2, 3's. I've got right side written with all A's and B's, 1, 2, 3's. All I need to do is algebra, 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 and show that left side is equal to right side. Now it's just brute force. So you don't want to watch me just do this. You could do it yourself. I'm going to ask that you do kind of multiply it out yourself. Yeah, you're just going to go, you're going to lie to me and fast forward through the video and not look at it anyway. But it does work. Maybe you should do like one component just to try it out. Just like, it's not that bad. But if I were to multiply this all out, first times first plus second times second plus third times third, simplify it all down, I'll get a left side expression. So I'll have some function with all the A's and B's and 3's and 1, 2, 3's. A's and B's with all the 1's, 2's, and 3's. If I expand this all out, I'm going to have the common denominator here. There's a lot of algebra, it's messy. But I'll get the same thing. So dot, dot, dot. I can show that left side equals right side from here. Put a piece in here. Left side is going to be this. So first times first, let's write this out a little bit. The first and the first are the same. So first times first, plus second times second. And since I'm squaring it, the minus and the minus will cancel, so I can just keep that piece. Plus third times third. So that's the left side. Expand this all out. The right side is equal to, I already have this piece here. Expand both sides out, and you'll show, it's probably better to do it. Expand both sides out and show that left side equals right side. So here I'm going to put the dot, dot, dot. That's for you expanding this left side out, expanding this right side out, and showing that they're the same. Then you've proven that the magnitude of these two sides are equal. So we've got another way of defining the cross product with the sign of the angle. Now, we did use the dot product formula, magnitude of A, magnitude of B, close to the angle between them. We used that whenever someone was talking about what's the angle between two vectors. Technically, we could use the cross product one also, but people don't. It's just the dot product is so much easier. You never use that for, or you hardly ever use that for finding the angle between two vectors. And this is only 3D, whereas the dot product works in every dimension. Okay. What else we got with cross product? We could use the cross product to calculate the area of a parallelogram. Okay, I guess we could. Say we wanted to. So here's a parallelogram. Got this angle. I'm going to call this vector A and this vector B. So this must also be B over here, and this must also be A over here, right? Because I can move the vectors, but it's a parallelogram. I want that area. If I were calculating this area in like just regular like any other math class without vectors, we would say, oh, I want to know the height here, and I know this height would be magnitude of A sine of the angle between them. And so the area of a parallelogram would be this length times its height. So our area, the area of the parallelogram would be this length, which would just be the magnitude of B, times the height, which would be, oh, magnitude of A, magnitude of B. Let's just switch those around so that they're in the right order. That's just the magnitude of A cross B, because we just made that formula. So if I want to get the area of a parallelogram, the parallelogram defined by these two vectors, I could just take their cross product and then find the magnitude of that cross product. Does that ever come up? No, not often. We can even, let's get that in right now. If I have two vectors, call this A, call this B, and I want to know what's the area of that triangle, well, that area of the triangle is just like half the parallelogram. This might turn out more. So that's going to be a half. The area of that parallelogram is magnitude of A, magnitude of B, sine of the angle between them. So I could use this cross product formula to find out areas of triangles defined by two vectors, I guess. Okay. Find the area of a triangle defined by the points. Oh, here's an opportunity to use our formula. But we've only got the points. So I need vectors. I need the vector that goes from this point 1, 1, 1 to the point 2, 0, 4. So let's call vector A it goes from 1, 1, 1 to 2, 0, 4. So that means the x component goes up by 1. The y component goes down by -1 because it's at 1 and then goes to 0. And the z component goes up by 3. So here's that first vector. We also need another vector that connects. Now which points? It doesn't actually make any difference. I just have to pick two different points. So I'm going to pick starting at the point 0, 0, 1 and going to the point 1, 1, 1. I'm choosing it. The x component goes up by 1. The y component goes up by 1. And the z component goes up by 0. I picked those because it makes the vector have easy to work with numbers, zeros and ones. And so when I take the cross product of them, my math would be easier. That's why I picked it. So I need vector A cross product vector B, and I have the component vectors, so let's just do our formula. I'm going to get 0 minus 3. I'm going to get 0 minus 3, but take the negative of that, so 3. And I'm going to get 1 plus 1, 2. Now, I'm going to check my work here. This has to be, because I'm going to use this in the rest of my calculation. Is this vector, minus 3, 3, 2, perpendicular to B? Yes, it is. Minus 3 plus 3, 0. Yes, it is. What about here? I get 3, minus 3 plus 6. Yes. So it makes me think my calculation is correct. Now I just need, the magnitude of that cross product. That would be square root of first component squared plus second component squared plus third component squared. So root 22 is the magnitude, and that would be the area of the parallelogram, but I want just the triangle, so I want half that area. So done. That's not too bad. Does not come up very often in real life, but it came up here as a use, an application for the cross product. Now this next question is a little bit more common, let's say. Find a vector perpendicular to the triangle. What triangle? Oh, the triangle that you made by these 3 points. But now it's defined by the triangle with the defined by these 2 vectors. So I want a vector perpendicular to the triangle. Well, all I need to get a vector perpendicular to the triangle is get a vector perpendicular to those 2 vectors. Oh, that's just the cross product of those 2 vectors. We already have that. So we made that as we went. There's our vector perpendicular to the triangle. It's also, a little bit of foreshadowing, if it's perpendicular to the triangle defined by those two vectors, it's perpendicular to, I'm looking around for a piece of paper or a pad or something, it's perpendicular to the plane that that triangle lies in as well. Okay, some properties of the cross product. So now we know how to make the cross product. We know two definitions of it, the component-wise and the one with trig in it. We know what it gives me a vector perpendicular to the two vectors I cross product. Let's look at some properties of that. The first property, A cross B is equal to, I'm not talking about the formula, but what I want to emphasize is that it's the negative. If A cross B is negative B cross A, we already talked about why that should be the case. Each one of these properties I could prove using the component definition by brute force, by just multiplying out left side and right side. This next component here, a constant times A cross B, what do I want to say with that? I want to say that that's equal to, I could factor the constant out, I guess is what I'm trying to say. And again, look at that component-wise. The C times the A vector means that each one of those, A1 and A2 and A3, is going to be multiplied by a C. So go back up and look at the definition here for cross product. If each one of these A's has a C on it, there's a C here, 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 there's a C here. I could just factor the whole C out and have it right there sitting at the end, and it would be C times A cross B. That's all I'm saying there. What about a vector cross product to sum? This is going to work like you think it works. That's going to be equal to A cross B plus A cross C. Got to keep the order the same. And again, we could prove that component-wise if we want to, but it works like I think it does. Now here's, what's the difference between these two? Well, this is cross-producting from coming in from the right-hand side. This is coming in from the left-hand side. But it's going to work the same. That's going to end up being A cross B, no, A cross C. Plus B cross C. And sometimes these properties help us simplify some expressions with the cross product. In the end, the main thing to remember about a cross product, besides the component formula and the magnitude of A, magnitude of B, sine of the angle between them formula, which is how to calculate things, the sort of fundamental thing to remember is when I take the cross product of two vectors, I get a vector perpendicular to those two vectors. And its magnitude depends on the angle between them and the size of the two vectors. That's sort of the main thing to remember.